I'll talk about our work, Online Boosting with Bandit Feedback. This is joint work with Elad Hazan. Our main contribution in this work has two implications, one being a new method for online boosting with noisy bandit feedback, and the other is a projection-free online convex optimization with stochastic gradients that improve state-of-the-art guarantees in terms of efficiency. In this talk, I'll discuss the second setting and then eventually describe how it yields our new boosting algorithm. So boosting algorithms typically combine weak or mildly accurate predictors into a strong predictor that has much better accuracy. This is achieved by iteratively calling the weak learning oracle with modified distributions over the data, and then combine those learned classifiers from each round and take the majority vote as the final predictor. This classic and widely known boosting methodology holds in the statistical and realizable setting. And a natural question to ask is whether it holds in other settings as well. Specifically, we consider the setting of online convex optimization, or OCO. So OCO is an optimization process that is sequential, and we have a sequence of convex loss functions, L1 to LT. We have a set of allowed actions, K, and at each round, the player is going to try to choose an action to minimize the unknown loss function. Then the player gets to observe the loss function. And the goal here is to minimize the regret, which is defined by the difference between the sum of losses incurred by the player and the sum of losses with the best single action in hindsight. In this work, we focus on a variation of that case, and specifically the case that the OCO cannot always fully observe the loss function L, and instead is only given some form of partial information about L. To motivate this setting, we can think of, for example, applications such as reinforcement learning or submodular optimization, when only partial feedback is available to the learner, or that computation steps are very expensive. So more concretely, in such settings, we often have these two main challenges. So first, it is often the case that exact gradients are unknown or are unfeasible to compute. And the second challenge is that computing a projection onto the constraint set is often very expensive or even infeasible, since it requires solving a quadratic optimization problem in each round. So to circumvent these issues, our goal is to design a projection-free OCO when given only stochastic gradients. So before I get into describing our online algorithm, let me start by describing projection-free optimization in the offline case. So first, let's assume access to exact gradients. The algorithm that is mostly used in this case is the Frank-Wolfe algorithm, and I'll demonstrate how it works in this illustration. Okay, so imagine this is our action set, or the convex constraint set K. And let's say that at iteration t, we are at this point xt. So to get to the next point, we'll compute the gradient of our loss function L, and find another point in the set K, let's call it Vt, that is the minimizing point in the direction of the gradient. And then we're going to look in that direction and step a little bit towards it. And that is our new point xt plus 1. So we're going to continue that way for t iterations towards the minimizing point of our function in this set. And the important thing to note is that we always pick points that are already in our constraint set. So the need for projection is eliminated, and we have a projection-free optimization algorithm. Okay, so now the question is, can we make this approach to work with stochastic gradients rather than exact? And by stochastic gradients, I mean any unbiased estimator of the gradient so that it equals the true gradient in expectation. So a straightforward way to achieve that would be to just replace the part in the algorithm where we use the exact gradient with the unbiased estimator, the blue term here. But this fails, and this is the reason why Frank-Wolfe-type algorithms don't easily admit stochastic gradients. And to briefly explain why that is the case, we need to look at the update step of the algorithm. So this step where we find the direction vt, that's the minimizing the gradient, and this step is not robust to noise. And we can show that if the gradient estimator is very noisy and it has a high variance, this step can lead us very far from the actual vt. So even if we have an unbiased estimator for the gradient, the step that we take forward may be very biased. Or in other words, this is just the fact that expectation and argmin are not interchangeable. Okay, so how did previous work handle this issue? It is by designing algorithms that are based on the Frank-Wolfe algorithm plus a variance reduction technique that requires a large cost per iteration. So in the table, you can see that the last two works that have a square root t regret, they have a very high cost per round that is linear in t or worse. Our approach achieves the regret bound of square root t as well, with a much lower cost per round of square root t. So our algorithm maintains n instances of online linear optimizers, or OLOs, A1 to AN. And each OLO instance is a black box oracle that is just any online optimization algorithm for linear loss functions with sublinear regret. And this can be online gradient descent or projection-free variants of it, such as follow the perturbed leader. Then our algorithm for each time step t iterates over all OLO oracles, A1 to AN. So in every round t, the OLO oracles are each fed with an unbiased estimator of the gradient and make a Frank-Wolfe-type step forward, as we've seen before. And our algorithms takes a convex combination of those and outputs the combined point. And this continues for each time step up to t. So the analysis of our algorithm is based on the Frank-Wolfe technique. But we are able to show that by using this structure, where each OLO is encouraged to correct for the mistakes of the previous OLOs, so we can entirely eliminate the high variance that is caused in the situation that I've described before. So as I've mentioned earlier, our results achieves an algorithm that is a projection-free OCO, which admits stochastic gradients with only square root t cost per round. And this result holds both in expectation and in high probability. And the implication of this result in online is an online boosting algorithm for regression problems with partial information. So to intuitively see how these ideas yield a boosting technique, notice that the OLO oracles can be replaced with a weak online learning oracle that is only an approximation to the best predictor in hindsight. And the resulting OCO is a strong or boosted online learner. Then, instead of stochastic gradients, we can use a zeroth order optimization technique to obtain a stochastic gradient estimation. And by that, we generalize to the more challenging Bandit feedback setting. Overall, we achieve a new method for online boosting with noisy Bandit feedback. Thank you.